Welcome to this explainer. If you're a first-year student just getting your hands dirty in the electronics lab, well, you are in the exact right place. We're going to totally demystify RC circuits today. We'll start with the physical nuts and bolts reality of the components themselves and end with what I like to call their absolute superpower, filtering frequencies. Let's kick things off with a pretty high-stakes question. What actually happens if you plug a polarized capacitor into your breadboard backward, or if you push its internal electric field just a little too far? Spoiler alert, it blows up. Literally. But to figure out exactly why that happens, and more importantly, how to harness that incredible electrical power safely, we're going to follow this quick roadmap. We'll cover the anatomy of capacitors, the RC time constant, shaping the square wave, and finally, filtering with RC circuits. Let's get to it. Starting off with section 1, the anatomy of capacitors. We got to look at the physical container itself and see what's actually going on under the hood. Take a look at how the electric field behaves between those two pairable plates. We've got a dielectric material, basically just an insulator sandwiched right in the middle. Now, if those cleats get too close together, or if you crank the voltage too high, that electric field gets overwhelmingly strong. The dielectric material just straight up breaks down. You get a spark jumping between the plates, and boom, the component shorts out and is completely destroyed. So, to avoid these explosive little failures in the lab, you absolutely must pay strict attention to these three crucial specs on the packaging. You need the capacitance value, the maximum voltage it can handle before that breakdown occurs, and whether it's polarized or non-polarized. Seriously, crossing the positive and negative leads of a polarized cap is a guaranteed way to make it pop. Alright, moving on to section 2, the RC time constant. Let's see how throwing a resistor into this setup helps us safely control all his stored energy over time. When we flip the switch in this basic schematic from position A to position B, the system instantly springs to life. The current starts out at its absolute peak, but then it drops off and dies out exponentially. At the exact same time, the voltage across the capacitor starts completely empty at 0 and rapidly climbs, curving up to basically meet the source voltage. For your lab calculations, you really need to know exactly how long that charging takes. And honestly, the math here is kind of beautiful. When you multiply resistance in ohms by capacitance in farads, the units cancel out perfectly into seconds. This gives us our time constant, which we just refer to as RC. Which brings us to section 3, shaping the square wave. Now that we've got a handle on a simple switch, let's hit our circuit with a much more complex input, a square wave, and see how that RC time constant physically shapes the signal. On the left, we've got a perfectly clean square wave input. It snaps sharply back and forth with a set period, which we'll call t. On the right is our simple RC circuit. The output we get is going to depend entirely on the relationship between our time constant and the wave's period. We're going to look at 3 different scenarios here. We'll start with condition 1, a balanced state where our RC time constant is roughly equal to the square wave's period t. Notice that second graph down. When RC is about equal to t, the capacitor has just enough time to charge and discharge before the wave flips on it again. It's constantly playing catch-up. This smooths out those hard square edges, giving us these really cool curved shark fin shapes. But what about our second condition? What happens if we drastically speed things up and the RC time constant is way smaller than the wave's period t? Well, looking at that third graph, when RC is much less than t, the capacitor charges and discharges incredibly fast. It hits its maximum almost instantly, essentially perfectly mimicking the original square wave input. The signal just breezes straight through. And finally, we have the third extreme scenario, condition 3, where the time constant is much greater than the wave's period. Down in that bottom graph, look at how restricted the voltage is. The capacitor barely has a fraction of a second to react before the signal aggressively changes direction again. The result? A nearly flattened output just hovering right around 0. That powerful square wave has essentially been blocked dead in its tracks. That blocking effect leads us right into section 4, filtering with RC circuits. This physical ability to shape and block waves is the foundation for filtering specific frequencies. To wrap your head around going from time response to frequency response, think of it this playground swing analogy. If you push someone on a swing slowly at just the right low frequency, you get this huge smooth movement. But if you start pushing them super fast, a high frequency, the swing just jitters around and barely moves at all. Our circuits do the exact same thing. Remember, Frequency is simply the inverse of the period t. A low-pass filter lets low-frequency signals cruise right through. That happens when RC is much less than t. A high-pass filter is built to do the exact opposite, letting only those rapid-fire signals through. So if you're wiring up a low-pass filter on a breadboard, it looks exactly like this. The input hits the resistor first, and the capacitor acts as a trapdoor straight down to ground. High frequencies fall right through that trapdoor, leaving the low frequencies to safely pass on to your output. But flip those components around. Put the capacitor first, followed by the resistor going to ground, and you've just built a high-pass filter. Now, the capacitor acts like a wall to slow, steady signals, but allows those super fast high frequencies to jump right across to the output. It's totally wild how two basic components can completely shapeshift the fabric of an electrical signal, right? So, I'll leave you with this to chew on before you head into your next lab. How might these exact same simple RC filter principles be the invisible force shaping the deep bass and the crisp treble in your favorite headphones right now? It really is all connected. Thanks for hanging out with me for this explainer, and keep exploring.